Welcome everyone. In the last video we saw why cavities are used as a resonator at microwave frequencies. We saw that at microwave frequencies normal LC resonators or inductor capacitor resonators do not work well, so microwave cavities are preferred for performing resonating functions. Now in this video we will see another type of cavity resonator, that is re-entrant cavities. So what is a re-entrant cavity? A re-entrant cavity is generally speaking a type of microwave cavity where energy is stored inside the cavity not in the first attempt but after the re-entry of the impressed signal. The difference between a re-entrant cavity and normal cavity, that is rectangular cavity or circular cavity, you will understand more when we see or when we will study clystrons later on. But right now let's talk about re-entrant cavities. As the name suggests, re-entrant, the impressed signal is entered again inside the cavity. So at a frequency well below microwave range, the cavity resonator is usually represented by a lumped resonant circuit that is made up of inductors and capacitors. But when operating at a very high frequency, that is in microwave range, these inductors and capacitors must be reduced to their minimum order, that means their minimum value, to maintain the resonance at the operating frequency. So how to achieve this minimum value? Usually inductance is reduced to a short wire, capacitance is reduced to a open wire. Therefore, since we are using wires for this representation, we can use transmission lines or waveguides for creating these resonator cavities or cavity resonators. Therefore, these re-entrant cavities are designed primarily for use in the clystrons, as I said, and microwave triodes. What are the clystrons and triodes? We will see that later in the syllabus. But these re-entrant cavities are not used for simple general purpose cavity resonator. These are designed for use in klystron amplifiers like reflectrons, magnetrons, and so on. So in the re-entrant cavity, metallic boundaries are extended into the interior of cavity. So how they are extended into the interior of cavity? We will see that usually we combine two short cavity resonators or small cavity resonators in different manners and create a re-entrant cavity. So there are several types of re-entrant cavities. Let's see their geometry for once. On your screen you can see there are 5 types shown. The first one, this one, it is coaxial cavity. That means it is a combination of two coaxial lines separated by a gap. This line represents a gap between the two coaxial lines. This is coaxial line 1 and this is coaxial line 2. Then second one is called as radial cavity or circular re-entrant cavity or rectangular re-entrant cavity, where two waveguides, rectangular or circular, are combined together by again a small gap. So this is a gap, this is a gap, and these two are the waveguides, or they may be transmission lines also. Then third one is a tunable cavity, where it can be tuned through this particular what we can say is a knob. It can be tuned to a particular frequency using this particular adjustment, so it will be a movable one. So desired resonant frequency can be obtained using that one. And there will be a toroidal cavity, which is this one, which is primarily used in the reflex clystrons. Again there will be a gap. You will see in each one there are gaps to provide impressed signal, and there will be two cavities which will be able to store the energy upon the re-entry of the impressed signal. Okay, toroidal cavity, again here there will be impressed signal and it will be used in the reflex klystron. For example, here there may be a reflector. The working of this klystron we will see later on. Once the reflector reflects the impressed signal, then cavity can store the energy. Then last one is the butterfly cavity. Again there is a gap here which is able to combine two different cavities. So there are several types. These are some of them. Now in this video we will discuss only about these two cavities. It's not used. This is just an introduction for re-entrant cavities. The use of this re-entrant cavity will be seen in the clystrons, as I said. So we will focus on these two cavities, coaxial cavity and radial cavity. So let's see what is coaxial and radial cavity. So first let's see the geometry of the coaxial cavity. This is the geometry that is shown in figure A, where you can see there are two coaxial lines. This is first one and this is second one. Now since this is a cavity, these coaxial lines are shorted at both ends, here as well as here, so that it becomes a cavity, but these are now separated by a gap. Now we have seen in the cavity resonators, each part of this cavity resonator will act as an inductor or capacitor. So these coaxial lines, which are mentioned by these numbers 1 and 2, these act as an inductor, and the gap between these two coaxial lines act as a capacitor at microwave frequency. So you don't have to use lumped elements, inductors and capacitors for microwave frequency, and this behavior remains same for very high frequencies. So this is how resonator can be obtained using two coaxial lines. So this type of structure is known as re-entrant cavity. So if you take a cross section of it, that is a view from this side, and if you cut it in the middle, then you will see this type of configuration. These are the two coaxial lines and this is the gap between them. Okay, so now the dimensions have been shown. This L denotes length of a coaxial line. This is the length. Then A is a radius of a coaxial line, 2a is the diameter, and 2b is the diameter of a exterior wall, we can say, or whatever that is covering the coaxial line, shielding the coaxial line. Okay, Zin is the input impedance provided by the combination of these two outer walls or shieldings. Okay, so this is a cross section of a coaxial cavity. So let's see how resonant and what will be the resonant frequency supported by this. Then there is a geometry of radial cavity, also called as rectangular or circular cavity, re-entrant cavity. Again, these two are this one and this one. These are cavity or waveguides which are combined by this gap with a width of d. This is a gap. Again, gap acts as a capacitor, and two cavity waveguides or two cavities act as a inductor to provide the re-entrant cavity. Okay, separation between the two cavities or two waveguides or two transmission lines should be 2a. Okay, so this is radial cavity. So let's see how, at what frequency they provide the resonance. Then there are several geometries you will see. Toroidal cavity, which is primarily seen in the reflection klystron. We will not go in detail about this one. Again, as I said, in the gap we are applying here we are applying the impressed signal. Here there will be a reflector which will reflect the signal, and the energy will be stored in these two cavities. Okay, so we will see that in the reflex klystron. So let's talk about coaxial cavity and resonance frequency associated with it. The characteristic impedance of the coaxial line is given by Z0 is equal to 1 upon 2 pi square root of mu upon epsilon natural log of b by a. The notation of b and a we have seen. B is a, or 2b is a diameter or total distance between the two outer walls, and a or 2a is a diameter of a is a radius of coaxial line. Then mu and epsilon are general notations, permeability and permittivity. So in the coaxial cavity, in the coaxial line, there can be a dielectric medium also. So if it is a free space, it will be epsilon 0. If it is another dielectric medium, it will be epsilon 0 into epsilon r, that is epsilon. So the coaxial cavity is similar to coaxial line, shorted at two ends as I said, and joined at the center by a capacitor. This joining of a center by capacitor is not actually placing an capacitor. There is a gap between two coaxial lines, and this gap acts as a capacitor. Okay, the input impedance to each shorted coaxial line is given by Zn. That means input impedance of this one and input impedance of this coaxial line, both will be Zn. That is given by Jz0, that is characteristic impedance, into tangential of beta L. Beta is a propagation constant and length is a length of a coaxial line. Okay, so if we substitute this Z0 into this equation, we will get revised equation for Zin as Zin equal to J upon 2 pi square root of mu upon epsilon, like natural log of b by a into tan beta L. Simple substitution will do the trick. Then the inductance of the each cavity is given by L, that is given by this formula 1 upon pi omega into this term, and the capacitance of the gap, as I said, gap represents the capacitance. It's not actually a capacitor which is placed in between them, so it is represented by Cg. It is given by this formula epsilon pi a square upon d. Now once you know these two values L and C, it is very easy to find out the value of omega or resonant frequency. Okay, so if we take this omega onto the left hand side, it will become omega L. Okay, if I take this omega onto the left hand side, this becomes omega L. So that is nothing but inductive reactance. Okay, similarly, if you have to calculate omega Cg, that will be capacitive reactance. And at resonance frequency or resonant frequency, magnitude of inductive reactance and capacitive reactance both are same. That means omega L is equal to 1 upon omega Cg. Okay, so using that formula we can calculate the resonant frequency. So as I said, at resonance, the inductive reactance of the two shielded coaxial lines are equal to magnitude of the capacitive reactance of the gap. So if we do that mathematically, that is omega L is equal to 1 upon omega Cg. So thus tan beta L, so let's go back to this one. So we have a tan beta L over here. If we rearrange that, taking these terms onto the left hand side, we can find out value of tan beta L. That will be equal to 1 upon omega Cg, because omega L into this term will be tan beta L. So let's do that. So what we will get, tan beta L is equal to d into v. This is not a derivative, this is d dot, that is into v. V is a phase velocity which is given by 1 upon square root of mu epsilon, and that's why you see a square over here, because we are having mu into epsilon for phase velocity, and in our formula we have mu upon epsilon. So that rearrangement can be done to obtain this particular equation for tan beta L. Okay, so since the equation contains tangent function, that means whatever waves that are incident or impressed on this thing, the resonant frequency will be, or number of resonant frequencies, not a single one, because they will be tangential to the direction of the or geometry of the coaxial line. So it has an infinite number of solutions with larger values of frequency. Therefore, this type of re-entrant cavity can support infinite number of resonant frequencies or infinite number of modes of oscillation. Okay, one thing to note, cavity resonators are mostly used in devices which requires oscillators or resonators at microwave frequencies, because at microwave frequencies we are not using lumped elements because their behavior is unpredictable. So to achieve that resonator or oscillator at microwave frequency, we are using these cavity resonators. So if we use re-entrant cavity at such microwave frequencies, it can provide infinite number of resonant frequencies. So it is very useful coaxial cavity. And it is also shown that this shorted coaxial line cavity stores more magnetic energy than electric energy. Okay, so it is all observed that magnetic energy stored in the coaxial cavity is comparatively more than the electric energy it can store. The balance of stored energy, that is balance between electric and magnetic stored energy, appears in the gap for resonance frequency. So at resonant frequency, in the gap, electrical energy stored by the coaxial lines is equal to magnetic energy stored in the gap or capacitive energy. So both will be equal. So that's why we have derived this conclusion that capacitive reactance is equal to inductive reactance at resonant frequency. That means both are storing same amount of energy. Lines, if we combine energy of these two lines, that will be equal to energy stored in the gap. This will be a capacitive and this will be inductive. Okay, so that is coaxial cavity. Now let's move on to radial cavity. A radial re-entrant cavity, as shown in figure, is another commonly used re-entrant resonator. Which figure? Let's go back to radial cavity. This is toroidal. So this is a radial cavity. Again, as I said, these are two waveguides, and this is the gap. Okay. So what is the resonant frequency for this one? Let's see that. The inductance and capacitance of radial re-entrant cavity is expressed by the given formulas. Now again, inductor is represented by the waveguides, rectangular, or that may be circular also, and gap represents the capacitance. So again, the same concept, just the geometry is different. Okay, sorry, this is not a gap. Inductance is represented by the cavities, so two cavities which are combined. So inductor is given by L is equal to mu into L. L is a, again we have to see what is L in the geometry, natural log of B by A, and C is given by this term, slightly longer formula or complex formula. The resonant frequency, again using the same concept, if the omega L is equal to 1 upon omega Cg, you can find out this resonant frequency. It is found out to be in this formula. So if you observe, it is raised to minus 1 by 2. That means this term divided by this entire term, which is in the curly braces, and it will be a square root raised to 1 by 2, where C is not a capacitor in this case, because this is a small c, not a capacitor, capital C. C is a velocity of light in a vacuum. Okay, so the function of a radial cavity is similar to that coaxial cavity. Only difference is in coaxial cavity we are using cavity as a coaxial line or coaxial line as a cavity, or in radial cavity we are using waveguides like rectangular or circular waveguides as a cavity. Okay, so that is the only difference, otherwise function will be same. So that is all about re-entrant cavities. That's all for today. Thank you.